Here I'm going to talk about what the fundamental theorem of calculus means, and not so much how to get it here at least. So I'm going to start with a very simple example. Here is the graph of a line. This is y is equal to 1. And I'm going to treat this just as a regular graph. But what I'm going to do is do what I've been doing and try to find the area of this. Now fortunately, since this is not a curve, dividing this up into a series of rectangles and then finding the sum of those is very easy, because these are all going to be of area 1. But that's not really the point so much. What I'm going to do next is plot x versus the area over here. So I'm going to start x is equal to 1. What is the area equal to? I only have one square, so this is just 1. So the area is equal to 1. Of course, 0, 0. That's a simple one as well. So for x is equal to 2, now I've got 1, 2, so the total will be 2. And then next I have 3, 1, 2, 3. Each one of these is area of 1. So this graph will look something like this. It's just a straight line. So next I want to look at what this graph is. This is just a graph of a straight line. This is y is equal to x. Now the next thing I want to notice is that if I take the derivative of this function, it's equal to 1. And that is what this graph is. This is a graph of y is equal to 1. So I've shown a relationship between the area underneath a curve of a function and also that of its derivative and the area versus the x values. So I want to do one more example. So here I have another simple graph, just y is equal to x, just like the one above. Now I want to do the same thing, and I chose y is equal to x is because it's very easy for me to get the areas. So if I want to do a sum of the area beneath this curve as x gets larger, so here I'm just going to divide them up into triangles, another easy shape for me to deal with. And all I'm doing is going to plot x versus the total area underneath the curve of this function. And the area of a triangle is equal to 1/2 base times height, or height times base, doesn't really matter. So I've got 1, 1, 1/2, so it'll be 1 and 1/2, so right there. Next I'll have 2, 2 times 2 is 4, 1/2, so 2. Then I've got 3, 3 times 3 is 9, 1/2, so 4 1/2, so it's all the way up, it's like up here somewhere. Put these together, and it looks very much like y is equal to x squared. But it's not quite y is equal to x squared because it's half of it. If it was y is equal to x squared, it would be 1, 4, and then 9. But I've got 1/2, 2, and 4.5. So this is the graph of y is equal to 1/2 x squared. And again, if I look at this function and I compare it to this function, and then I take this function's derivative, bring the 2 down, this will cancel out, and then I'll just get x. So one thing I'm beginning to notice is that the sum, or the integral, of this function over here is equal to whatever this function is over here. So the area underneath this curve is equal to whatever the functional value of this is. And similarly, whatever the derivative of this function is equal to this function value over here. So if I integrate this left side, it's equal to this right side. If I take the derivative of this right side, it's equal to the left side. So I want to do one more example that will, and this is more of an intuitive example that people should be able to understand without any really prior knowledge in math. So if I think of a velocity problem, let's say I'm turning this next problem into a velocity problem. So I've got some velocity. Let's say this is 10 miles per hour. So this is velocity, this is time. Let's divide this up into 1, 2, 3. If I want to know how far this has gone, someone has gone in 3 hours, and I just know its velocity, this problem is easy because they're always going 10 miles an hour and it's a constant. Then I can say, well, 1 hour they've gone 10 miles an hour, 2 hours another 10 miles an hour, 3 hours another 10 miles an hour. And then I add all of these up and this is 30 miles an hour. Or just, well, 30 miles. Forget about the hours. So they would have gone a total of 30 miles. So when the velocity is constant, it's easy. But what if I were to do the same kind of, or ask the same kind of problem, but with a curve like this, where it's not easy for me to say, well, they're going 10 miles an hour the whole time, so I just multiply it by 3, and then I've got, my answer. Here I would have to use the Riemann sum approach if I didn't know anything else. What I could do here is give an estimation. I can find out what the average velocity of here was. So this is something. Then I add it to this one, 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 then I add it to this one. And that would be an estimation of what their distance is. What adding all of these up gives me is the distance. That's my point. So what I did was I added all these little squares up, and this one was easy because they're already rectangles, and it gave me the distance. I could hypothetically do the same thing here, but here it would be an estimation. But with my integrals, then since this is a limit as n goes to infinity, then it actually gives me the area under the curve. But what my point is that this area under the curve is the distance traveled, just like this example. This is the distance traveled. When I take the area under the curve, when I know the velocity, it gives me the distance. So one thing I wanted to use the velocity example for is that distance and velocity are related. If I take the derivative of distance, this is equal just to the velocity. And what I just showed here, though, is that if I take the area under the curve of velocity, though, it gives me the total distance. So what basically this means is that if I integrate velocity, let's say, then it gives me the distance. That's basically what the fundamental theorem of calculus is doing. And one more relationship, since if I integrate velocity, it gives me distance. Hold on, what was I doing? Oh yeah. If I integrate velocity and it gives me distance, if I replace velocity with the derivative of distance, I forgot that. Then basically taking the integral undoes what the derivative does. So that's the link between the integral calculus and differential calculus. So this is basically the fundamental theorem of calculus in a nutshell. It allows me to link derivatives and integrals, and basically now when I think of some function f of x, I can either think of it as its functional value, or another way of thinking of it is the net change in its derivative, and it's the same thing really. And that's what this net change in area. So this area is equal to its distance is equal to the distance traveled. So what I'm going to be able to do is if I take the derivative of something, I can undo that by using an integral. So this is basically, as I said, this is just basically with as little math as possible what the fundamental theorem of calculus is about.